I'd like to say a few words about Charles Davidson. Charles is a graduate of the School of Chemical Engineering in 1972. In fact, he followed his mother's footsteps, who was not a chemical engineer, but Hazel Terrell graduated from the university in 1925. So she was certainly one of the earlier women graduates of the university. After graduation, Charles joined Arco Oil and Gas Company and was with them from 72 till 1988. And later, with that same company, was in Arco, Alaska, and was the senior vice president for the Eastern District for the years 1992-93. Now, the year 1993 was an interesting one because he was a member of an executive team that formed what was called Vastar Resources, and he joined with that team to form that as an offshoot of Arco, and was in fact the president and CEO of that Vastar Resources during 1997 to 2000. And in 2000, then he joined the present firm that he's with, Noble Energy, as president, CEO, and chairman of the board, and he's been in these positions since the year 2000. A word about Noble Energy itself. It's one of the leading independent energy companies. It's engaged in exploration and production of oil and natural gas. In 2010, for example, its assets were $13 billion, revenue sales of $3 billion, and this is an important point, the income was $725 million. Now, if you just make some arithmetic, it is a 24% income on the sales. We should all invest in Noble Energy. I'd like to do that. He, after also subsequently during the course of his working with Arco, he received a master's degree in management from the University of Texas in Dallas in 1981, and where he also met his wife Nancy, and they're celebrating the 30th year this year, and both have received that school's Distinguished Alumnus Award, as Chuck has received from Purdue also the Outstanding Chemical Engineer and the Distinguished College of Engineering Alumnus Award in the year 2000. He is also involved in various professional and community organizations. I'll say just a few. He's, for example, has been the chair of the Independent Petroleum Association of America's Offshore Committee, and also the former chair of the so-called Domestic Petroleum Council, which is the independent producers of oil and gas in the country. He is also engaged in the community affairs. I'm saying a few things to give you a picture of Chuck and his involvements. He's, for example, the past chair of the Society of Performing Arts for the city of Houston. So you can see his wide range interests, not only just professional, but also community-wide. And also the chair of the Sam Houston Council for that area, Council, Boy Scouts of America. So very engaged in the profession, in the community, leading a major corporation with extremely good income. He has also been and these are the final words I would like to add, a major donor for the Chemical Engineering Capital Campaign, and particularly for the renovation part of the older building. And in fact, in honor of Chuck and Nancy Davidson, we have the conference room, which is 3059 in the older building, the Charles and Nancy Davidson conference room. And just a few weeks ago, we have named the administrative offices for the School of Chemical Engineering also in their honor. So they are now called the Charles and Nancy Davidson Chemical Engineering Administrative Offices. So we certainly want to thank Charles and Nancy for their generosity, and really looking forward now to his Centennial seminar on the topic mentioned. Charles, please.
Thank you very much. Well, it's great to be here, and thank you for that kind introduction. It's, I will tell you that it doesn't seem that long ago that I was in your spot, but not in such a nice facility, but here, and I never would have dreamed that I would be back to talk to students, graduate students, undergraduates, and faculty of the School of Chemical Engineering. So I think it, just as a reminder, as all of you, some of the students that are here, as you think about your future, anything is possible, even coming back to Purdue to present in such a wonderful occasion as we're all celebrating the 100th year anniversary of the School of Chemical Engineering. So again, Dr. Varma, thank you so much for inviting me to be here and to talk on my favorite topic, which is energy. And so I will launch in. Now, I've warned a few, I certainly warned some of the faculty, you are not going to see any calculations, formula, equations. There's no quiz, no test. But we will have time for Q&A afterwards. So why don't I just launch in? We saw a little bit at the beginning about Noble Energy and who we are, so I won't go into a lot on that. It is an old company. It's just a few years ago celebrated its 75th anniversary. It was formed back in Oklahoma as a private company and went public in the early 70s. I'm really proud to be a part of this company today as it's continued to grow from just being a domestic company today. It's a company that's pretty much balanced with about half of our production being in the United States and half of it being in international. We're traded on the New York Stock Exchange. No, I am not here to sell stock. That way I don't have to put up this big, long legal disclaimer at the end, but we are on the New York Stock Exchange, and at last look, our market capitalization is about $17 billion. We have just under 1,800 employees worldwide. A lot of engineers and a lot of geoscientists, as you would imagine, in an exploration and production company. Our major core areas are shown on this slide. The 4 red areas are what we call our primary focus areas. They're in the U.S. onshore, in the U.S. deepwater Gulf of Mexico, in West Africa, where we operate in Equatorial Guinea and Cameroon, and of all places in Israel, which I'll touch on a little bit at the end, but where Noble has been privileged to basically be the only company to discover hydrocarbons offshore Israel, and is in the process really that discovery of changing that country and creating a possibility of energy independence for it that's never existed before, but a little bit more on that later. We are an upstream company, which in our world means that we look for it. But our job is to find it. And it's getting hard to find, so it really takes a lot of technology to find it. But we look for it, we find it, we develop it and produce it. That's about where it ends. We get the natural gas and oil ready for market, sell it to market. We don't do refining, we don't do marketing. You won't see any filling stations with Noble Energy on it. We are primarily an exploration company that once we find it, we'll develop it and produce it and then hand it off to others. So let me talk a little bit about the energy environment, and then I want to then move in and talk about what I think are some of the important technologies that's changing the upstream energy business, both here in the United States as well as internationally. The top of the list, for those of you who do watch energy in the U.S., the whole name of the game is natural gas and how it's changed. And so today, we are seeing new resources being developed in the U.S. as a result of shales, which here before just a few years ago were viewed as really non-productive, non-commercial sources of natural gas, that today shales are changing the landscape in the United States. And as a result, we're now finding that in terms of natural gas, the United States has moved from a country that at one time expected to be importing a lot of natural gas to meet its needs to, as I'll show in a moment, a country now that potentially could export, but at a minimum has probably 100 years of supply, all based on technology. We're moving to oil because oil has value, and as a result, there's a lot of work that's being done in oil projects, both in the United States and international. Over half the wells now that are drilled in the United States are drilled horizontally. The traditional thinking about drilling is you drill this vertical well, and you finally, if you're lucky enough and you find a hydrocarbon reservoir, you produce it out of this vertical well. Well, that is in the past in terms of work that's done in the United States. Through technology of horizontal drilling and completions, we now drill over half the wells in the United States horizontally, which means that there are a lot of reservoirs, including these shale reservoirs, that are productive where in the past they weren't. Also, I'll talk a little bit about deep water. It's an important part of the industry, certainly had a major impact. We're now just literally on the the anniversary of the terrible incident in the deepwater Gulf, the BP Horizon Macondo incident, and the industry is just now getting back to work. I know that for Noble Energy, we're very proud to be the first company that was given a permit to resume drilling, ahead of a long list of majors, but we worked very hard with the government. And I'll show one of the systems that we helped develop that allowed us to get the first permit to return to work. And then finally, just to keep in mind that energy is a global business. It's not just what's happening here in the United States. And so today, we're seeing that things that are happening in the Middle East and even things that are happening in Japan are having a significant impact on global energy markets. In the Middle East, it's caused oil prices to move up sharply with a concern of restricted supplies from countries such as Libya. And in Japan, because of what's happened with their nuclear industry, they're having to supplement with other energy supplies, primarily liquefied natural gas and some other fuels, and that also is putting pressure on the market. So it's clearly a global market. So as we go from, and we look at things, we've seen a lot of headlines, certainly for people like myself that study the news, but we're seeing U.S. gas fields that have been transformed many times because of horizontal drilling. We're even seeing now new oil fields onshore U.S., again because of some horizontal drilling. This example being the Bakken, of all places in North Dakota, which may turn out to be one of the largest U.S. Onshore fields developed in recent years, where just a few years ago it was viewed as uncommercial, and now is viewed as perhaps holding recoverable resources of several billion barrels of oil. We don't have to be reminded about commodity prices, but there was something I wanted to show here to give as an example. This shows commodity prices, natural gas, crude oil, and two kinds of crude oils. Crude oil traded in the United States called West Texas Intermediate, and another crude oil that's called Brent, that's basically tied to a North Sea oil. And there's a difference there. But one thing you can see is you go back to 2008, we had very high prices of both oil and natural gas, record prices for those commodities. The recession hit, and demand for energy dropped, and those prices fell. Now, there's not very many businesses can continue on when they see their primary product, the price of it, drop more than in half in the course of just a few months. But that's what's happened when we saw oil going from over $140 a barrel to around $40 a barrel in just a short period of time. What's important that I think is a message in this slide to look forward is to what's happened with oil and natural gas prices since the bottom of the recession. We see oil prices moving back up. In fact, West Texas Intermediate today is at right around $110 a barrel, and Brent is actually over close to 125. And the reason is Libya and some of the other things that are happening in the Middle East has actually put more pressure on some of the international oil prices than on the U.S. oil prices. But look what's happened on natural gas. It's gone basically nowhere. And it's today priced at about $4.50. On an energy equivalent basis, natural gas is priced about 25% of what oil is, which I think creates tremendous opportunities for this country, because imagine going and filling up your car at $1.39 rather than $4. But that's the kind of potential that may exist here, especially if we're successful in moving more natural gas into the transportation sector. The reason the price is low is we have a huge abundance of natural gas in the United States because of our ability and the new technologies that have unlocked all of this gas from the shales. So what do I, when I talk about energy just a little bit, I have to be careful because I've been living and breathing this for a number of years, so I get caught up in lingo. I'm always reminded of that, and they say, what in the world are you talking about? Even my wife reminds me, what did you just say? So in the Q&A, if I said something, if I used too much lingo, just make sure and ask me to explain something. But just a little bit on conventional versus unconventional, because it's important in our business. Conventional oil are those sources that we've thought about for many years. They come from places like onshore oil fields, even deep water, frontier exploration, but it's conventional being that they're produced, they're drilled in conventional means. Unconventional, which is, I think, a great opportunity, gets into some of the things such as heavy oils. Mentioned there bitumen, some of the extra heavy oils from Canada and Venezuela. That's where new technology is really starting to unlock these resources, and there's some huge resources there. Also coal to liquids and gas to liquids, some of the things that the School of Chemical Engineering is focused on some of its research as well. On the gas side, you've got conventional gas from legacy fields, and in today's nomenclature, unconventional usually means gas from shales, gas from some things such as tight reservoirs or coal bed methane. You can actually produce gas out of coal seams, and all of that is being developed as we go forward. So where are we on energy? I'm not a proponent of so-called peak oil. I believe we have a lot of energy in the world, and if you start out and you look at global conventional and you look at the third bar down from the top, it's this bar that's right here. And just to give you an idea of what is being shown here, this bar represents in billions of barrels, so that's a little over 1.1 trillion barrels have been produced through the end of 2009 globally from conventional. This is what's projected to be produced through 2035. This is what today is estimated to be the proven global resources, and this is what is estimated to be the total recoverable global conventional oil resources. So if you just look at that, we probably just on that chart have perhaps at least 80 more years of supply of oil. And the reason that I believe that's more than enough is one, this is not the end of the story. This is just a snapshot of what we see today. Two is I'm going to show you another slide of the unconventional global oil resources, and that presents a whole different picture. And then finally, I think we all believe that we will become more and more efficient in using energy going forward, and at some point, the absolute use of energy will start to decline as the efficiency catches up. The unfortunate thing, it takes a long time to replace things like our fleets of vehicles that turn over very slowly. The other thing probably to point out here is we're more challenged in North America, where you can see here's what we have produced, here's what's proven, this is what we need through 2035. So on this chart, you would say we need to either become more efficient or we're really destined to continue to import oil, at least at the rates we're talking today, unless we can do things like switch to natural gas that would help relieve the pressure on imported oil. But let's look at unconventional. And that's a different picture. If you see there what is in oil in place, perhaps some 8 trillion barrels, 8,000 billion barrels, 8 trillion barrels, technically recoverable, who knows? It's all technology. Today you look at it, the estimate is maybe there's 2,000, 2,500 billion barrels that are technically recoverable. It still takes a lot of work to get it out. But what that does mean is that even if we do that, we've perhaps got another 100 years of supply. So I'm not a believer that we've got peak oil at all. I think all we've got is we've got technology limits and that we need to open the doors. So let's talk a little bit about where we go. And I want to first touch on gas and then talk about some of the technologies. But when you look at natural gas, you get a different picture. First of all, it's probably 150 years of supply globally. Natural gas has a lot of advantages. If you look at it in terms of generating electricity versus coal, it has half the carbon emissions when it's generating electricity versus coal. It's obviously, on a carbon count, one of the best fossil fuels to use. And it is plentiful. You look at the world, again, probably 150 years of supply. North America, I would say that this is a world energy outlook. There are some that believe that it's probably getting closer to 100 years of supply just in the United States and North America on gas. And so as a result, We've got abundant resources, and it looks like we can be self-sufficient for natural gas for some time. Shales. Shales are the reason for that, and actually the shales are becoming a reason for on the oil side as well. This just shows some of the shale deposits that have been identified and are now being developed throughout the United States as well as Canada. Some of the big ones, the Marcellus, which is a gas shale in the east. The one that really started it off was the Barnett here near Dallas-Fort Worth and the Haynesville, the Fayetteville. My company is involved in the Niobrara up in Colorado, which is both oil and gas. So a number of shales. We've actually drilled some wells in southwestern Indiana in the New Albany Shale. A lot of new resources which 5 years ago no one really considered as productive. The EIA several years ago had an outlook for natural gas in the United States, and it was not very encouraging. It showed that conventional gas would continue to be with us, and we'd have this amount of unconventional, which at that time was basically coal seam gas and tight gas, and then we would have to supplement that with imports. And so the outlook back in 2005 was that over the course of the next 10 or 15 years, a quarter of the natural gas needed in the United States would be imported. And as a result, companies started building LNG regasification plants. A number of them were built along the Gulf Coast, and they are there today, and they are not being used. Because what happened, if you fast forward to just the one that was put out recently by the same agency, is that the unconventional shales have suddenly blossomed, and now the projection is that we'll only need about 1% of our natural gas being imported, and all the rest will be made up primarily from unconventional. We still have got unconventional tight and coal bed methane, but the big chunk here is this unconventional shale wedge that didn't exist just a few years ago. All driven by technology, exploration technology, drilling and completion technology. So what I'm going to touch on in the next few minutes is what I think are 5 important technologies that are helping drive energy, global energy, here in the United States and throughout the world. Enhanced recovery, which is all that's about is getting more out of existing reservoirs. The best place to find oil and gas is in an existing reservoir. The exploration risk is gone. It's then to an engineering challenge to get more out of it. Drilling, where there's clearly been some huge advances in how we drill as well as how we complete wells. Deep water, an area that was not really 15 years ago that accessible to us, and now we can go into deeper waters where there are hydrocarbons, but we didn't have the technology to drill or produce them in the past, as well as exploration technology. So let me quickly move through these to give you a bit of a flavor of what I think are some of the leveraging technologies in our industry. And first, enhanced recovery, and this is one that, again, I think is one that sometimes we miss, and that's just getting more out of an existing field. This is a field that Noble Energy operates, and it goes back into the early 70s, and I could assure you, I wasn't there at the time, but I can assure you that people were thinking as they were developing this field that that's probably all that was going to be there, is what they had started developing. But then they went back in and they redeveloped some current zones. These are the names of different formations that were in the field. And then they kept adding things on. So as a result, rather than a field that started out and then started declining, because subsequent technologies and redevelopments, you've actually been able to greatly improve the field. And I think now the story is just starting over again, because this is a field where now we've started to drill horizontally in it, and it's going through another whole life cycle. So enhancing recoveries of fields are very important. So is heavy oil, and I mentioned that as part of an unconventional oil source. This is something that my company is not involved in, but clearly an important area is in Canada, and you can see that if you just look at their conventional sources, it's pretty limited as you look out in the years, but by adding The unconventional, the heavy oils, either through mining or through in situ recovery processes, they've got a tremendous ability to improve recovery. Again, it takes a lot of technology. This is certainly more energy intensive than conventional means, but it can add a lot to oil supplies into the future. So if you look at just where Canada is today, you can see that in terms of total oil resources, conventional and unconventional, they would estimate they would be around 175 billion barrels, of which most of it is unconventional, but that would put them up with Venezuela and Saudi Arabia in terms of a comparison against those countries' oil resources. So important, but a lot of work that needs to be done. Unconventional takes, again, as I mentioned, a lot of energy, and it takes evolving technology, and clearly the commercial threshold is higher than for conventional oil. So one of the things that's happened as we've seen higher oil prices is it's allowed the industry to develop some of these unconventional sources that in the past they would have passed by. This just shows a picture of some of the operations that are being used to develop these, both in situ as well as mining. On the drilling side, no, we're not using these anymore. That goes back to the beginning of our industry, and that was in the 1900s, Spindletop, close to Beaumont, Texas, where you just lined up the rigs next to each other, and the way to maximize recovery was just put more holes in the ground. Well, fortunately, we don't need to do that anymore, and today's rig looks a lot different. These are 5 rigs that are under contract to Noble Energy today. These are what would be 5th and 6th generation deepwater rigs, generally construction costs of $500 to $600 million, capable of drilling. One of these rigs is capable of drilling in up to 8,000 feet of water. So it's a different world, but it's opened up the deep water environment, and it's opened up a lot of opportunities for us throughout the world. We've got 2 of these operating in West Africa, 2 in Israel, and then 1 of them is operating in the deepwater Gulf of Mexico on that permit that we just received. Not only do we move in deeper water, but we're drilling to greater depths. And so you can see here, for deep water drilling, typically when deep water drilling started in the mid to late 70s, 15,000 feet was a deep well. Now it's not unusual to be drilling 30 to 35,000 feet in terms of total depth that you've drilled on a well. And that may be in many times in water depths of 5,000 to 7,000 feet. So the technology has allowed us to access reservoirs that are a few years ago were far below the drill bit. The other thing which I mentioned is horizontal drilling. And so today we can drill down several thousand feet, turn a corner, and then go out thousands of feet horizontally, which gives us more flow area in a reservoir, which allows us to change formations that at one time were not commercial, and suddenly today are commercial because we can have a long extended wellbore in the reservoir. In the Bakken up in North Dakota, there are instances where they've gone as far as 8,000 feet in length after they've drilled down several thousand feet to get to the reservoir. So as I mentioned before, horizontal drilling has really caught on. This just shows the percentage of horizontal drilling, and today it's approaching 60% in the United States. The other thing just to note here, this is the total drilling in the United States, total rig count. Of course, this was a peak we saw in 2008. It fell with recession, but now it's climbing back to where it was. So we have a very active program in the United States today. But it's a very different program, driven by horizontal drilling and the development of unconventional resources. You look at well completions, again it goes back to horizontal, and this is an example of one of those horizontal wells, and now we're able to not only drill these horizontally, but we've actually able to stimulate by pumping in water and sand through the whole reservoir interval. And so not only do we get this long well bore of flow surface area, but by being able to stimulate with water and sand, we can open up more area in the reservoir and greatly improve the productivity. So in the case of For instance, in the Niobrara in Colorado that Noble Energy is developing, a horizontal, it's not uncommon that a horizontal well bore will ultimately recover 10 times what a vertical well would have recovered. And this is just another example of how we've taken these things and again being able to stimulate and complete along the entire distance of the wellbore. A big transformation from just a few years ago where we could drill the horizontal wells but we couldn't complete them. All we could do is just open them up to the reservoir and produce whatever they could, but we couldn't stimulate them. And that just shows an example of a production of a horizontal well. This is a typical vertical well. These are some of the better horizontal wells. So it not only improves the overall recovery, this is the ultimate recovery of each of these wells, but it obviously improves the flow rates initially, which improves the returns of the projects. So we go to deep water, and so we've shown that we can drill in deep water, but how in the world do we produce things at 5,000 or 6,000 feet? So I included some examples from our own portfolio. Now the real technology is putting production operations on the sea floor. And so this is a subsea operation where the wells, the producing wells, are located in 6,000 plus feet of water on the sea floor, and then they flow back to a central processing facility. Maybe several fields might flow back to the same one. So again, you've got the synergy of a single production facility, perhaps in shallower water, but able to locate all your production systems on the ocean floor, not having to put a lot of surface systems and having to put a lot of connections between the sea floor and the surface, which actually has got some safety advantages as well. So this is an example that we're developing in the deepwater Gulf of Mexico. This is one that we're developing in Israel, where we're laying out a whole field and then flowing it a long distance to a fixed platform here. Another one that we're doing in West Africa, where we're actually taking a ship, a converted oil tanker, and it's being used to process oil that's produced through these subsea systems. It processes the oil, stores it on the ship, and then other ships come to pick up the oil and transport it, never having to take it to an onshore location. Everything can be operated from offshore. Again, opening up a lot of new opportunities in the international arena. And the final example, this is again in West Africa, where we've got a combination where part of the field is in deep water, so we develop it using subsea systems, flow line it back to the shallow water portion of the field where we can process it on fixed platforms. This is if you've ever seen a picture and people talk about Christmas trees, that's the tree that you have on the surface with a series of valves that you produce oil and gas from the well. This is today's modern version of a Christmas tree. This is one that will actually be headed towards about, it will be in Israel in 5,000 feet of water. Very sophisticated systems. The oil and it's gas in this instance. The gas will be produced out of this and controlled by the system there, but again, all sitting on the ocean floor. So a lot of changes. I mentioned earlier that Noble Energy was the first company to receive a permit to go back to work in the deep water, and you know, I have a lot of admiration for our technical teams that work very hard. We had two choices. One was we could bury our head in the sand and deny that it would ever happen to us. Or two is we could go and we could work with the other industry and the government and develop systems such that we could not only reassure the government but the public that if such an incident did happen, that we could respond to it. So this is a system that's in place now that is available. This one has been developed by a company called Helix, along with today about 25 other companies, including Noble. And so what it allows us to do is, if heaven forbid another incident like what happened with BP were to happen, rather than to sit and try to figure out over the course of 2 or 3 months what to do, we first of all designed the well that we're drilling such that this system can be put on it. There was, without getting into a lot of technical details, there was some real problems with the BP well. You couldn't just go ahead and cap it off. You might have other subsurface problems. But the wells now are designed that you can bring in a capping tree to put it in and do that in a course of days rather than weeks or months. And if that isn't adequate, we also have now built and contracted systems such that you can put this tree in. If you don't feel secure in shutting it in, you can flow it and produce everything to the ship so that it doesn't flow into the water. This, along with a number of other systems, the application for this particular well was over 2,400 pages long. A lot of documentation just on things like what would be the maximum flow rate in a blowout. It was actually a Purdue engineer that early on recognized that that well was flowing at a much higher rate than what was being estimated. And today, just the flow calculations for our permit were 900 pages long to go through and truly understand what's the flow possibilities. And then, most importantly, be able to design these systems and design the well so that you can handle it. So a lot has happened. It's not just that the industry has sat by and waited till somebody finally gave them a permit, at least not in our case. We have spent the last year developing a number of systems and increasing the capability to improve the safety, which I think is just critical. I'll finish up on exploration and then I'll open it up for questions. And exploration is probably a little bit foreign. This is the hard part for me as a chemical engineer. This does not come natural. It's a part of the business that's driven by geophysics and geology, understanding really how oil and gas was created back millions of years. And some of the people that are explorationists are true artists. They're scientists as well as artists in terms of being able to envision how these systems come together. This is a field that we discovered in the deepwater Gulf of Mexico. It's called Gunflint, and it's a challenging one. It's in 6,000 feet of water. It's 29,000 feet below the surface of the water. It's very large, could be up to 500 million barrels in size, but it's very complex. It's a subsalt reservoir, which means that not only you're drilling through all these sediments, but you've got salt surfaces, and then you have to drill below it. One of the most complicated things that you can look for in our world. And I would say that 10 years ago, it was almost impossible to explore subsalt because the two things, we didn't have the geophysics, but we also didn't have the computing capability to handle the amount of data that's necessary to understand these, because it is a massive, usually you're talking about supercomputer capabilities to handle the 3D seismic imaging that we get out of this. But today it's quite a different picture. We don't have a week, so I'm not going to explain this picture, but I'll try to give you an idea of what it's doing. This is a seismic image. It was actually based on a 3D seismic survey. And it's the section, this is the area that we're looking for, and what these are these are amplitude maps of as we've propagated sound waves down into the earth, and based on how they reflect, it gives you an idea of structure, whether you're seeing some structures. It can actually sometimes give you an indication of hydrocarbons. What's made this so complex is you've got all these salt features here. And the only way this works is if this is what's called in depth. In other words, just how is this shaped in depth? But that's not the way seismic works. It's in time. It took so many seconds or microseconds to go from here to here. And guess what? The velocity through salt is different than the velocity in these sediments. And so getting these shapes exactly right will change this whole picture. So being able to transform something from time to depth is an incredible complex challenge, but it's one that's, I think, really opened up some of the subsalt reservoirs throughout the world. We have now, our discoveries both in Israel and the deepwater Gulf of Mexico are both subsalt reservoirs driven by this new exploration technology. This was an image of Gunflint back in 2006 using the best technology we had then. And I was foolish enough to buy the lease off that data, and we did. We were the successful bidder. We had about 7 other companies that were bidding for it. At the time, I thought we spent far too much for it, and we couldn't see anything except they just said, looks like there's something in there. And you saw the prior image as to what it looked like. Things have changed a lot. That's what's called a narrow azimuth 3D. I won't bother to explain that. It has a lot to do. But today, when you look at the new wide azimuth with new processing, some of it proprietary, we can actually start to see, this is all blown up, we can actually see the individual formations. In fact, this is now tied to the discovery well, where we can actually tie these reflectors into the individual zones that we found in the well. An amazing difference, I think, attributed to not only the seismic industry, but also the computing industry in being able to do this. So it's, we do other things. We take seismic and we process it. We can actually calculate the thickness of reservoirs using some inversion techniques. This is an amplitude map. The hot areas represent the thicker parts of the reservoir. So guess what? We put our wells in the thicker parts and we avoid the thin parts. It makes more efficient development there. This is in Israel. This is a tricky word for just salt. This is where the sea evaporated many years ago, created a salt layer. We went down below it and found a reservoir and natural gas, very large deposits. In fact, the 2 largest deepwater gas wells found in the world in the last 10 years have been found in Israel by Noble at this prospect. And at the time I showed this map, we hadn't drilled that, but guess what? That was a discovery as well. So I'm waiting to get over to that one. That one is a Cyprus prospect. So I think it's, just in wrap up, it's the technology is just continuing to evolve. Don't forget natural gas. Don't forget natural gas here in the United States. Don't forget it globally. It could be a really important bridge as we move from oil to alternatives. And there's no doubt in my mind we will move to alternatives, but it is abundant, it's globally available, and it is something that's very important. It's important not only for generating power, but it's important in our petrochemical industries to both use oil, use natural gas, or use it as a feedstock for other things. And the fact that its cost has come down and its abundance has gone up is rapidly changing the U.S. chemical industry as well. We've got to be very focused on regulation and access. I touched on what we've done to respond to the Gulf of Mexico incident. And then finally, just a final note is this is an industry that has not done a great job of planning for its workforce. We went through a period where it was booming in the early 80s, then the oil prices collapsed in the mid-80s, and as a result we didn't bring the people into our industry, and we are scrambling today. On the upstream side, because really between the mid-80s and the late 90s, we did not bring enough new talent in our industry to help us get over the next coming decades. And so there's a lot of opportunities in the upstream energy as we go forward. We've got a lot of catching up to do as folks like myself are getting grayer hair and have graduated from schools 30 plus years ago, are trying to decide how long are we going to stay hitched on this versus do something else. But it's something I love, and I also love being here at Purdue. So thanks so much, and I will certainly open it up for questions. Yeah.
Open for questions, and we ask the students first.
I was wondering, what was the motivation for using a tanker as a rig on the one platform?
Oh yeah, on where we use that, it's called an FPSO. The reason for that is it's all self-contained and you don't have to build a lot of facilities on shore. And so by being self-contained, and I would say this is in Equatorial Guinea where it's very difficult to build new things. It's actually offshore an island. It's in deep water. So it'd be very expensive to try to transport all that oil to shore and process it and then build a facility to load tankers there. So it's cost efficient, and in my view, it's actually safer because you avoid long transportation of oil and natural gas to shore. So it's an example of what you can do in deep water.
I was just curious, you talked about horizontal drilling a lot, and they're showing a lot of pictures with 90-degree bends on the pipe. I was wondering, how do you bend the pipe and make it go where you want it to go?
That's the graphic artist. They get magic like that. No, actually, they can have some. It's a more gradual curve than probably is shown in the artwork, and given the scale we've got, this pipe is actually pretty flexible. So you can get it. A lot of times you may set some pipe just before you start the bend, and then you start the curvature, and you can actually work it around in a curvature. So the scale is a little different. When you start thinking about over a mile, this pipe is actually pretty flexible, so you can take it around. But it's not as sharp as what it's shown on that picture. It makes it all fit on the slide nicely, doesn't it? But it's a more gradual curve, so that it stays within the flexibility limits of the pipe.
But how do you tell the cutter head to, I guess, start changing direction? That's all new technology as well. They have steerable drilling systems now, and they have remote sensors on it and we actually have logging packages so that we can tell exactly where that drill bit and that steering system is, and by controlling the hydraulics that go down to the bit, they can actually steer that assembly. And not only do they steer it to make the curve, but then as they're going out horizontally, they can steer it and keep it flat, because generally the formations will try to push it up or shove it down or move it around. So it's a combination of remote sensors that tell you exactly where you are, along with the systems that you can actually then, a lot of times through hydraulics, drive it a certain direction.
Right.
Do you think we can ever increase our production rates in the U.S. and oil enough to affect global oil prices?
My first reaction would be say no, but then I'm thinking about it right now, and we've already done it. And that in the slide I showed, if you saw that the WTI, which is the U.S. oil price, is about $10 below global prices. And the reason it's below global prices right now is we have a huge amount of supply of oil, particularly in the mid-continent. It's because of some of this, a lot of it is due to some of the shales that we're developing, and particularly the Bakken up in the Rockies. So we can maybe lower our price some against world supply, but it's very difficult with the demand that the new economies, such as China, are putting on global oil. And that's, I think, the biggest challenge we've got, is that they put so much demand on it that regardless of what the U.S. does, their growing demand for energy is having the most impact on global oil prices. So the answer is maybe we can affect it some. The perfect example is natural gas, where we have totally disconnected from the global market. It doesn't matter to us today what global natural gas prices are. In Asia, natural gas is probably going into that part of the world at $10 or $12 per million BTU, and it's $4.50 here in the U.S. because we found enough gas that we've detached. Right now, I just don't see the U.S. as being completely able to detach from the global market on oil unless we can substitute our use of oil for something else, such as get more natural gas into the transportation system or something like that. It's going to take something other than just finding more.
You talked a lot about the role of technology in alleviating some of the safety concerns, as well as alleviating some of the supply concerns as far as the exploiting oil and natural gas. With your permission, I'd like to ask you for your opinion on a more controversial topic. What do you think the environmental impact would be in exploiting or harnessing these resources? For example, do you think technology will be able to alleviate some of the environmental concerns with regards to harnessing oil and natural gas resources?
Good question. I think clearly technology helps in one way on the environmental concerns, and that is in improving the safety of the operations themselves, because one of the concerns is the safety of operations. I talk about horizontal drilling, and today in this country there's concerns about the use of hydraulic fracturing, and clearly technology, to me, the leveraging area for technology there is in water reuse. I think that the industry has to move to where it 100% recycles the water it uses in completing wells, and that's one of the big concerns from the environmental community, and one that all of us are working to answer, and it's one there's a technical solution there. It's already starting to happen where we're recycling water, but we need to do 100% recycling. And so that's the case there. Also, in just production of oil and gas, it's important in things such as fugitive emissions to be able to get to where you've got zero emissions. In our operations in Colorado, we've invested a lot in a special system such that we can eliminate fugitive emissions, because in many instances it's the methane escaping that can impact. So all of those are important, as well as moving to cleaner fuels. Moving from coal to natural gas has a huge positive impact on the environment. Nothing is perfect. That's why I talk about, at some point you've got transition fuels that help move you to alternatives as well. But I would say we're using technology not only to find, but also to reduce the impact and to improve the safety as well. And it's a very appropriate question.
So basing off of that question and your answer, so in the frac case, there is some leak of natural gas. Can you just comment on that becomes larger scale and a more dominant technology, what the impact methane might have on the atmosphere would be?
Well, I mean, the impact on methane in the atmosphere, the key is if you've got it being emitted as methane, and the point there is to reduce down the so-called fugitive emissions. Basically, you produce it and you put it into a pipeline, and then the impact that you've got of methane is just like any other fossil fuel. It's combusted. It has the advantage that not only does it have lower carbon emissions per unit of energy, but also a lot of the other things that come with heavier fuels aren't associated with methane. So it's actually, of the fossil fuels, the cleanest to use. I think in terms of hydraulic fracturing, the real issue that has to be addressed is the water usage and the water disposal coming out.
So I had a question about this. So we have a lot of natural gas now. Historically, over the last 100 years, whenever we found a lot of a resource, it's led to people trying to capitalize on that as soon as possible, and that inevitably leads to a lot of waste of resources. How do we keep people from recklessly using the natural gas and keeping this efficient rather than just selling as much as possible to make as much money in a short period of time?
Yeah, I think when you look, there was a number of years ago, there was a concern that we were running out of natural gas, and so we had some legislation. It was a Fuel Use Act that basically said, don't use it in any boilers. Now that was limited, and it was eventually eliminated. But I think that in an economy that is driven by supply and demand, right now we have such an abundance of gas that I don't think, it's hard to envision that it's going to be produced too fast or wasted, because
it takes so long. Most companies have a 40 or 50-year inventory of drilling opportunities alone, so it's a very long-lived process. And the types of things that I guess I would hope that would come out of it would be some policy changes that would favor using natural gas in the most leveraging ways. That's why I'm a proponent of transportation. Probably not automobiles initially, but there are certainly heavy fleets like the local delivery trucks. This would be like the UPS trucks or those that generally stay in an area that could use natural gas, and the impact on the environment is tremendous, and they actually get a cost benefit. But we've got to get the infrastructure, and it takes some policy changes to put the infrastructure in. So a number of us in the industry are advocating putting in some of the infrastructure. One of my peers recently in Houston built and donated to the city of Houston at the Houston airport a natural gas refueling station such that all the airport vehicles could be converted to natural gas. When Noble in Israel found natural gas, it was the first gas in that country, and we started delivering it to the country, and we actually helped them build the infrastructure. We started producing in 2004, and between 2004 and last year, the emissions that were reduced as a result of using that natural gas in their power systems were the equivalent of them shutting down all their automobiles for a year. And that's over a fairly short period of time. So there's some tremendous value, but in many instances, we've got to get the infrastructure in place, and that's going to take some policy changes. And we'll take some investment, too.
I should add just one word here, because I go to India quite often. I'm from India originally. So in India, in the large cities, Delhi, Mumbai, etc., in the large cities, most of the taxis and city buses are all run on what's called CNG.
Yep.
It's compressed natural gas. So that's actually how they run.
It's actually
much less emissions of smoke and stuff that used to come before. So in fact, in some parts of the world, it's going on actually, because we do not have so much in this country.
I'm glad you pointed out, because actually the United States is very unique. That when you look at gas vehicles globally, as Dr. Varma pointed out, many countries are far ahead of the United States in terms of their so-called CNG fleets, or compressed natural gas fleets. In the U.S., it's almost nothing. And the reason is we've had this plentiful supply of gasoline. It's been easy. In other places, gasoline prices sometimes for taxation reasons have been higher, and it's driven the use of alternatives. And so it may be time for change. Yeah.
My question is about the potential job opportunities in Noble Energy. So is Noble Energy hiring any PhD or master's student with a degree this year?
We hire some every year, generally BS and MS, and we hire chemical and petroleum. This is because we're located in Texas. We don't, even with my influence, I can't direct everywhere we recruit, so I don't think we have a recruiters at Purdue, but we do have a broadband, and it's a nobleenergyinc.com. Thank you.
Let's thank Davidson for this very
Oh, well, thank you, everyone. Thank you.